have the next speaker, Joshua. Joshua Beaker, who is a security analyst at Riskia. Joshua will share applicable defensive knowledge of preventing a large amount of fault injection attacks with only software. His talk title is Proving the Efficacy of Software Countermeasures for Fault Injection. I would personally like to thank Joshua for presenting a countermeasure talk at our conference, because it's really difficult, I know, when it comes to securing hardware. And for me, over the past 5 years running hardwear.io, most of the submissions via the CFP comes on offense, but very few on the defense and countermeasures. So thank you, Joshua, for doing this amazing research and also sharing it with our community at hardwear.io. Over to you, Joshua.
Hello?
Yes, we can hear you.
Excellent.
And see you as well.
See my screen and stuff, I can go?
You can share your screen.
Is that shared?
We can't see your screen.
Okay.
No. Yes, now we can see it. Yes, go for it.
All right. Okay, so hi, I'm Josh. I'm new to this. I'm from Detroit, Michigan. I work remotely for a company called Riskia, and I have a rhetorical question for all of you. So have you ever wanted to seem like really cool on the internet by hacking into a really secure device with very little effort? Well, sorry in advance, but I'm about to. Sorry, can you hear me? Is there a noise? Okay,
it's fine. Yeah, we can hear you.
Sorry, 1 second. Let me just fix that real quick. Sorry about that. Okay, so I'm just going to restart this slide. So have you ever wanted to seem really cool on the internet by hacking into something? Yada, yada, yada. Sorry, I'm about to make that really hard. Maybe, hopefully. So if you haven't guessed, this talk is on fault injection countermeasures, specifically those implemented solely in software. So this talk, I want to prove to you that software countermeasures work. I want you to take away the ability to go pop open the white paper this talk is based on and be able to actually protect your programs from faults. And even more importantly, I want to sort of swiftly develop in you not only a sense of how faults work, but intuition on how countering them works. So when you go use this guide we've made to make your life easier, the white paper, you go, oh, of course, that makes sense. And you don't have to wander around blind trying to implement some logic that you don't fully understand. So, and yeah, also like even better, like 6 months from now, when you go, oh, that actually worked, but it can work better, you can contribute to the area and try to save the rest of us from awesome fault attacks. So first, we're going to have a extreme, super fast crash course on fault injection. And then we'll cover how to test the countermeasures in something called PhiSim and observe their mechanics, either logically or in the assembly. And then we're going to learn how to implement 7 different countermeasures and cover why they work. And finally, and this is where things get really good, we'll combine them and we'll combine everything we've done so far, and it'll be awesome. We'll make like a really cool little final example. So this is the slide where I set expectations about the material. So as you can see, I've created a thermometer on the right to demonstrate the heat or difficulty of the material. And the thin blue line in the middle is where our presentation will be. So from the bottom up, anyone should be able to understand the benefits or countermeasures by the end of the presentation. And even if you think like the costs outweigh them, you should be able to really understand like what the point of them is. To understand how the questions work in quotation marks, you'll need to grasp a teeny tiny bit of math and also how fault injection works at an extremely high level. And then to understand how to implement countermeasures, it will help to know the language that we implement them in, which is like C, so a little bit of C. And then, so that's where the presentation is. And then to go like above and beyond, to really, like in all capitals, understand the countermeasures, you'll need to know a little bit of ARM assembly. And then, but this will really only come up once or twice in the presentation. And then the rest will be in the GitHub repo, which I'll make clear later on. And finally, to make your own countermeasures in the future, you have to be enthusiastic about the information and just generally interested enough to go do it on your own. So, like I mentioned in the previous slide, all these countermeasures and more will be available in an updated white paper I posted today on GitHub. So that's the link on the top, and then in the future, it'll be the link in the middle. And then that's my Twitter. I'm super unpopular, so I put my Twitter. So this is like where the lectures start. So we need to talk a little bit about fault injection before getting into how to stop it. So fault injection on a practical and high level is using external disturbances to inject faults in chips by changing internal electrical state. So this change in state can either change data, so like memory, or it can change operations, so like opcodes and stuff. And that would like essentially change the actual assembly running on the device. And if you don't believe me, here's a video of someone cheating a slot machine with a little EM device. I won't play the whole thing, but down in the bottom left, you can see there's like a credit. And the hacker will then activate their glitcher. And so there we go. Yeah. So they're actually glitching the amount of credit that they have on the machine so they can play all night for free. So real world impacts exist. Yeah. So here's the only math you'll need to worry about. I'm sorry in advance. So on the left of this little equation, we have the probability that our external disturbance causes the intended fault. And this is dependent on our attack method. So it could be like electrical glitching, EM, stuff like that. And then on the right, we have the probability that the timing of our attack is correct. And this is really heavily dependent on two things. So there could be timing countermeasures, which you can read about in the white paper. We won't include them on this slide. Or it could be like the nature of the target and the attack method. And then a really high value in our general case on the left would be like 1%, and then really, really high value with like no timing countermeasures on the right would be 100%. And then this little N up here is sort of where our presentation, where we're going to operate in our countermeasures. So we're taking this, we're introducing this ability to put these probabilities to the power of N because N is the amount of faults that you need to accomplish a successful attack. So if you need one fault, N is 1, that's what we're normally used to dealing with if you haven't put any thought into FI in your software. But if you really think about it, you can increase that number, and that's what we've done. So this is our fault model. So a fault model is like how we're going to virtually think about our attacker. So for our fault model, it's going to be a single bit flip or skipping an entire instruction. So on the right there, you can see it could be like a single bit flip could be like changing the address by 1 bit to branch somewhere where you're not supposed to, or it could be changing a value moved into a register by 1 bit. And these are things that just so happen to allow you to, sometimes break into stuff. And then a skipped instruction would be, similar, but instead of changing a bit, you just completely skip the instruction. So instead of branching somewhere, you just go to the next instruction, which is whatever just so happened to be there. So to test our fault model, I have enlisted the help of an open source program a colleague of mine named Martijn created. FISIM is the name of it. The link's up there in the upper left. So this program's purpose is to evaluate some code, inject every possible fault according to our model, and then observe which faults successfully bypass the program's logic. So typically the code I use to test with FISIM is a version of Pine Boot that comes with it. But the purpose of Pine Boot code is to like take an image, verify it, and then continue booting. So when we talk about successful or unsuccessful faults, that's determined by if I can trick the checks in Pine Boot into booting when the image I have is no good. So with all that out of the way, we can finally look at our first countermeasure. So this is our first countermeasure. We call it minimal branches because its goal is to remove branches from your program. Specifically, we're targeting faults that seek to manipulate our program by glitching our branch instructions. So typically they'll either change the address of the instructions or remove the branch altogether, causing code to fail unexpectedly. This is kind of our example we had from before. So the countermeasure here is to make use of the inline attributes available in C to force our compiler to carbon copy our function logic where it would normally use a branch instruction. So surprise, we're starting off with like the first assembly or like one of the only assemblies in the presentation, but it's actually not that big a deal. So all you really need to worry about is in the red box over there, we have our branch instructions. This is our original code. And then with our countermeasure, you can see that we no longer have branch instructions. Instead, there's some logic in there. So the compiler has, just like we said, carbon copied the actual logic of the function in, and we avoid that sort of weak point where we can branch to random stuff with faults. So something to keep in mind, as far as results go, we see overall decrease in faults from 329 to 300 in our test. And then more importantly, the faults associated with the lines 30, 31, and 32, which is where our functions were being called, are completely removed. So as you can see, it's pretty effective at countering these types of faults. But something to keep in mind is that it can cost a lot of resources to inline a lot of really big functions. And then I thought it would be fun if I rated each of the countermeasures out of 5. So I gave this one no branches out of 5, so you all know that the ratings are a joke. So next up is one called flow control. The concept behind this is implementing a check that validates we've at least visited every function we intend to at a certain point. So implementing is fairly simple and involves 3 steps. You need some constants that can't be easily faulted. So maybe prime and not a single bit flip from each other. You also need one of those constants per function that you want to ensure the flow of. You need to add these constants to a rolling tally or a counter of some kind during the execution of your program. And then finally, you need to check at some point that the tally is a sane value. So this can be at the end of your program or before something critical. But the idea is that the attacker needs to fault both your check of the tally and something else to do with the logic of the program if they want to affect the flow. So, which they can't do in our fault model because they only have one fault. So I know that's kind of a tricky one, but if you're able to follow along, you have like a really simple tool you can use to essentially brute force an n amount of bit flips necessary to fault the flow of your functions. So the concept here is that for a number of implementations of this countermeasure n, the attacker needs n+1 faults to do any damage to the flow of your actual program before the checking point, right? So in our model, we would only need 1 check because we're observing our attacker to have 1 fault. And when we do so, we observe a complete recovery of all faults related to the flow of our program. More on this effect later. And then, and then some other notes. This is a pretty light countermeasure performance-wise, as it's just tracking some additions to our code, then an if statement at the end. So for a rating, I gave this one a Hoover Dam out of 5 because in my mind, the Hoover Dam controls the flow of water or something. So this slide's a bit of a two-parter. The goal is to address a common problem and assign values. So for the first part, we use non-arbitrary values for things. So the last thing you want is someone to be able to switch a 0 to a for fail to like a 1 for success. For the second part, we observe the ability to store sensitive values, possibly with a checksum or encryption, some kind of trapdoor to dissuade faulting when it's not being used, and then verifying them at regular intervals. The effect of this countermeasure extends, or the effects of the countermeasure extend the further you eliminate single bit flip targets. So for example, if you replace all your Boolean functions with complex values being returned, you'll see like a lot more effect than if you just change some if statements. And then in our test, the countermeasure completely alleviates all attacks on our simple values when we change them. And this one gets a dog food out of 5 because dog food is my favorite hex code to use as a success value. This one is decision check. It's seemingly easy to grasp, but naive implementation results in a pretty common pitfall that was one of the original inspirations for this deep dive into countermeasures. So we see the same utilization of checksums as before, but this time they have 2 jobs. One is to help trick the compiler, and the other is to protect us from simple faults. So what's going on is super simple. We're essentially checking things twice. In our fault model, only one of these checks could get skipped. So we can continue our code knowing we have some protection. It's easy to see how this one can work n times, right? So if you want this to work n times, you just check n times. So once, twice, 3 times, whatever. The pitfall, as mentioned prior, is this necessary volatile value for subsequent checks. So if you don't do this, your friendly neighborhood compiler will assume it knows better than you and try to fix it. So it'll optimize it out. So for those of you who don't know, volatile just specifies a value might be changed outside the scope of the program. So the compiler will always actually check it, and it won't assume it already knows the answer. Decision checks are really interesting. There isn't a complete reduction of faults on the affected decisions. This is because of the branch that happens at some if statements. We'll need an additional countermeasure if we want to get this to near 100. Decision check is relatively light, and it's just consecutive if statements. So it's easy to implement if the code's not sloppy. And then, so I couldn't decide what to rate it, so I just gave it a question mark out of 5. So aggregate check. I like this one because I think it helps paint a picture of some fault injection concepts. So whenever an attacker can fault one thing instead of 2 things, attacks become easier. We can see the top there is our bad or normal code. And at some point during programming, we decide, hey, later on, I only need to know if both or all of these checks pass. So let me just combine them real quick. Unfortunately, this gives our attacker a better chance to successfully attack. Our usage of these checks is counterintuitive. So the solution is to just not aggregate checks. One of the nice things about this is it's actually less code in some cases. We just have to handle a sort of gnarly, maybe exceeding your organization's line length rule if statement. So it's sort of just something to avoid. And since we have to check everything anyways, it usually doesn't slow our program down by much, if anything. So for the results, it can only target faults that affect the aggregated result. So we aren't looking at a massive change in the amount of faults, probably single digits at best, depending on the amount of checks we were aggregating. But of course, this is a great example to teach for beginners who, what to look out for. And then as for the rating, I gave it a checks together strong out of 5. And if you don't get that joke, it's because it's really obscure. So next is loop check. We're almost there. This one's really easy. We target faults that skip the amount of iterations in a loop or terminate it early. To counter, we simply check that the value of our loop counter is in a sane range. So if your loop needs to happen n times, you just write a check that it did. There's not much more to this one, which is nice. So as you can clearly see, it's fairly easy to implement, but it also solves a rare type of fault and completely removes that target, faults that target the amount of iterations a loop does, and about 48% of loops based faults overall. And as for the rating, I gave it a traffic roundabout out of 5 because they're both loops in which the only way out is forward. Okay, so we're finally at the last countermeasure we'll cover before combining them and seeing what we can do. It's an important yet extremely expensive one to implement. When faults affect encryption, they can not only corrupt the single process, but with multiple runs, they can reveal the key used in the encryption. So this involves some like seriously wizard math that we're not gonna get into, but to try and counter these attempts, we're going to decrypt directly after each encryption and compare with our original value. So another way to do it is like you could encrypt it and then encrypt the same thing multiple times and compare the results. But the concept here is we're just, again, the same overall concept through most of our countermeasures is make the attacker do something more than once. So you're verifying with multiple steps that your code ran correctly. As mentioned, this can get pretty costly. Encryption is already one of the larger chunks of runtime in a lot of programs, especially the ones we look at. So doing it more than once is a big detriment. On the other hand, it protects one of the most integral parts of the program, especially in code like bootloaders. But it's also necessary to protect any like on-system keys, which is obviously a really big deal. And then I gave this one a taxes out of 5 because we don't like paying the cost, but we really like the benefits of doing so. So that's the countermeasures. Congratulations. You successfully absorbed or try to absorb all the countermeasures I included. So take a second, pat yourself on the back, recenter yourself, because now we get to combine them and make Voltron, and it's going to be awesome. I promise. So this is where we really get a lot of our benefit, but also where a little bit of experience comes into play. So knowing which countermeasures to use, when and where, can require a bit of practice. Fortunately, practice is as easy as opening the demo project in FISIM and walking through the white paper. So combining countermeasures is always greater than the sum of their parts. Well, it's usually greater than the sum of the parts when you do it correctly. And in a lot of cases, the increase in code from simply implementing a single countermeasure can increase the total number of faults, which means an attacker is going to have an easier time simply randomly faulting your program, which is of course not good. So thankfully, combining them can alleviate this, as we're about to see. So our target is going to be the Pine Boot example that comes with FISIM. And to help illustrate the amount of faults at each stage, I've adjusted the font size of the number for the following results. So our initial fault amount is 327, which might seem like a lot, but I think if we stick to our guns and follow the guide, we'll see some seriously surprising results. So onto the first countermeasure. So at least I was right about it being surprising. So we've successfully added 22 possible faults to our code. And I don't think it can get worse. So let's just keep going. So 340 faults after 2 countermeasures. We just did crypto check. So that's better. It's still not as good as what we started with. So let's keep going. All right, so 250 is finally better than our initial fault value. And we only have 2 more faults to go. So let's just keep going. Sorry, 250, and then sorry, 268. So at this point, I'm thinking I don't like where this is going. So we've gone up right before the last fault we're going to implement, and we've only got one left. And I don't think there's a lot of space left on the slide. So as a thought experiment, ask yourself what you think will happen. Will the final value fit? Yeah, it will. So that's the last joke, I promise. So after all our work, we succeeded in dropping our fault total to just 8. And what's more, we only used countermeasures which have checks that can be implemented up to n times. So in theory, we can expand our fault model to n and still have around 8 faults. So what about only using flow control? Like obviously, there's a method to the madness of why I implemented the checks in that order. It's just easier code-wise to do so, but clearly flow control is some like, for our fault model and code more important. So what if we just use that? Well, it would actually only end up to be around between 32 to 48, depending on how you implement it. So as we're going through, which is still, 4 times, 5 times more than what we have at the end. So we are losing faults as we go. We're just also introducing other kinds of faults, which we're then subsequently countering. So what about the faults that evaded us? So first of all, we can take pride in our example that all the faults are bit flips. If they were NOPs, that'd be pretty embarrassing. Those are generally easier to get rid of. We've got 4 load faults. So these are actually in an entry.s file, which is just raw assembly, which gets ran, and we didn't countermeasure it. So it makes sense that they were faulted. We also have 3 subfaults, which are related to a function call, which I think might be fixable with a different countermeasure like minimum branches that we just didn't implement. And then we also have another branch related flaw, which is in our encryption code, which I think could also be maybe mitigated with minimized branches. So all in all, it's not bad. We've gone from 327 faults to 8 in our fault model. If you were attacking this with random faults, you would have a significantly harder time. I think this result really speaks volumes to the types of software countermeasures that are available for fault injection. And also, we really demonstrated that with the last countermeasure, the effect of combining our countermeasures. I like to use a leaky pipe analogy. So if you have a lot of holes in a pipe and you patch only one, you're just going to see increased pressure in other areas. And I know it's a flawed metaphor, but like it's helpful to think about it like that. So as you like always test your solution. So as you can see, just test your solution. You only really get the silver bullet when things really click into place. And we really saw like a good benefit when we went through that process and actually tested them out in our last example. So the cost for these countermeasures in runtime is not for everybody. It's important to weigh the benefits and keep in mind that some of the countermeasures play really nice with each other to counter faulting, but other ones like encryption check or timing countermeasures actually add other benefits that you might want, and despite their cost. So it's like keeping people from recovering your keys. So that's all I have today as far as learning goes. I wanted to take a few steps and talk about the next steps in this area. I think there's room for more research into compiler behavior in regards to FI, possibly even room to develop like a specialized compiler or compiler flags. I also think that there's a lot of countermeasures that exist that we don't know of yet. For example, I've been like every step through this process, I've found little things that just make things work better. For example, changing the Boolean returns to complex values while making this presentation. I found that while making the presentation. So completely after the research I had done. Also, I'd like to see different fault models in further detail to see if new properties emerge. And then I also think that we could do some tests in real life. So maybe like a bench other than like when we implement them into our products and see them work and stuff. So anyways, I hope you enjoyed my presentation on software countermeasures for fault injection. Please feel free to contact me or Riskier with any questions. And then I think we can start Q&A.
Thank you, Josh. Friends, if you have any questions for Josh, please send them on the Zoom chat. Yes, there's one question, Josh. Let me read it out for you. Do you have a countermeasure for someone inputting the Hoover Dam as a rating on a scale of 1 to 5?
Yeah. No, I don't.
All right. Should I go ahead, or you want to still respond to the first question? Okay. I'll read the next question, Josh, for you. It's from Jan William. Is it possible to just optimize the GCC compiler against fault injection and call it a day?
No. So obviously this field, so FI is in a way exhaustive in theory, right? So if you completely ignore the physical implementation and you have like alien technology and infinite time, it's exhaustive. You can completely rewrite the program using electro magic or whatever. So you can't like just you know, implement countermeasures and then, you know, never have to deal with it again for the rest of your life. So, and then another part of that is you can't solve all the faults that arise in the actual implementation just by changing compilers. So even if you were to make, you know, compiler flags, you'd need some kind of code syntax of where to implement them in some cases. And in other cases, you'd need a specialized solution anyways. So there's no way to completely call it a day just by changing the compiler. At least we haven't found it yet. So there's no, if you find it, like, awesome, please tell me. But I don't think that there will be that in the near future, at least. I know some people who have tried. I think I also have, you know, limited understanding of a lot of things, but that's my understanding.
Okay. There is a comment from Martin Russ. Excellent presentation. And there's one more question, Josh, from Jiang Fu. If turning on stack smashing protector is in compiler, will that improve FISM results?
Yeah, I don't know. Yeah, I mean, that's honestly a great question. You should email me that question. That's a good question that I can't answer right now.
All right, so Jiang, if you want to email Josh, it's beaker@riskier.com. So that's his email address. All right, there's one more question, Josh, from Munir. How often do you need to insert the fault countermeasure in the code? Does it not increase compile time, runtime, etc.?
Yeah, so it does. So maybe I should have been more explicit. The cost that we're talking about in the presentation is actually runtime, right? Compile time, runtime. So it's not like development costs. It's actually going to slow down your program. So if you have to run encryption twice, yeah, that slows it down. If you have to you know, unroll all your loops, that's going to slow it down. If you have to inline all your functions, it's going to slow it down. So as for sorry, I was reading the question and another one popped up. So as for how often you need to, that depends on the code, right? So like, I really want to stress that you have to test your solution. Like, there's no way to do this blind. If you're not testing your solution, I can pretty much promise it's not going to work. And it's going to be a different solution for every program. But I hope that with this presentation and with the white paper, which is at the GitHub, well, it's in the slides, so you can get it later. And with that, and maybe FISM as a test bench, you'll be able to like go develop an intuition for this sort of thing and make that solution for whatever you're working on. So it's going to be different. As like an average, I mean, I think the code for the test example I did for Pine Boot doubled, probably. So yeah, double the code. I think the runtime doubled or tripled. So not good in terms of cost, but really good in terms of fault injection. And if that's what you're really scared of, because you want to protect something really integral, it's probably might be a good idea. But again, it's also hard to really get down to what it's going to cost you until you implement it, which is another big downside because yeah, I mean, just the nature of it, you won't know what solution works and therefore the cost until it's done.
All right, Josh, there's one more question. If you could answer it, that would be nice, or you could also take it in the breakout room later on, but I'll read it out for you. It's from Robert. Did I understand that some countermeasures lowered FI results and any reason why? And the following part of the question is, for the final countermeasure test after flow control were all enabled at the same time?
Yeah, I can answer this one really quickly. So yeah, they were all enabled at the same time. So it's like a rolling result where we enable one and then do another and then another. If you do just flow control, it's in the range of like 30 to 50, which is, better, but not, the best, as you saw. And then, so for the other question, why they like made results worse, they're just implementing more code, which isn't countermeasured yet, because we're not using that logic from the other countermeasures yet. So if we have to do 2 if statements, this is kind of a bad example, but if you have to do if you have to inline all your functions, for example, which have faultable code in them, you're not jumping to it twice, or or like maybe your loops. Yeah, sorry, these are bad examples. Basically, you're just implementing a bunch of code, which is faultable, right? Until you do the countermeasure for that specific code. So if you're doing more if statements and they're faultable, and then you come back and you do another countermeasure that makes them less faultable with like flow control, then it makes it all come into place, kind of, if that helps. Sorry, I know that was kind of a bad example, but hopefully that helps.
All right, thank you, Josh. Thanks participants for asking questions as well. If you'd like to still interact with Josh, please join the breakout room now. There would be a pop-up onto your screen that says join breakout room. You could interact with Josh via audio as well instead of chat. So thank you, Josh, once again for this amazing presentation.